P1 on N is known as the distance between a point and a plane. Right, so yeah, so that's known as distance. But wait, give me a second first. This is in three dimensions, right? So is it? So is it the distance? I'm thinking, is that cos theta that's the distance or the component of P0, P1 on N? Hmm. Anyways, okay, so let's do this very. This might take a while. So I know that if I have a vector A and a vector B, I know that cos theta that's the angle between them is equal to A dot B divided by divided by A B. So if I say that the component of P0 P1 on N is equal to it doesn't look like it. Between a point and a plane. Let's keep going first. As equal to cos theta P0 P1. Yeah, I think I'm correct. Divide last line. So we can actually express this as a component of P0 P1 on N is equal to A dot B, so it's going to be N dot P0 P1 divided by magnitude of N and multiplied by the magnitude of that. And all of that is multiplied by, so it's all of this times P0 P1. Yeah, this is it. So it's times P0 P1, magnitude of P0 P1. So this one cancels this one away. So I have the component, this is equal to, so I have, okay, I'm gonna use this space here to write everything down. So I have the component to be going to be. And so the thing is, I'm very sorry because this is like, you need to have some initial knowledge about these things before you actually understanding it. So divided by. The normal vector. This is the distance. So keep this in mind. Later on, I'll show you more explicitly. So I have the distance to be. So P0, P1. So this is, I'm really sorry for doing this, but P0, P1 is you know what? Never mind. So N is defined to be AX plus BY plus CZ. Is that? Sorry. N is defined to be AI plus BY, BJ plus CK. Alright, and P0, P1. And then the shape for this one. P0, P1 is a direct, it's a line with 3 space. P0, P1 is defined to be X minus X0I plus Y minus Y0J plus Z minus Z0K. So if I do the dot product of these two, so I have that, I have P0, P1 dot N to be, because if you put dot product of two vectors, you have this a scalar function. So I have, okay, so I'm just going to put all the coefficients into the brackets and see what we have. So we have, note that A, B, and C they always given vectors, they always given numbers. So this is just the general form. X sub 0, Y sub 0, Z sub 0 are always given numbers, right? So this initial point, which is P0, initial point of this the initial X coordinates of this point, initial Y coordinate of this point on this plane, initial Z coordinate of this point in this plane. So those are numbers, and AI are directrix, the numbers, the direction vectors. I'm just going to put all the numbers, all the direction vectors into P0, P1 so you can see what's happening. So I have a number multiplying a variable minus a number multiplying another number plus a number multiplying a variable minus a number multiplying another number, and I have plus a number, C, multiplying that variable minus a number multiplying another number. So let's call so we have equal to AX plus BY plus CZ is minus AX0, make it bigger, is equal to AX plus BY plus CZ minus AX0 plus BY0 plus CZ0. Know that these are numbers multiplying numbers. So that's a constant, that's a number. So we have, this is equal to AX plus BY plus CZ minus a number small d. Right, so that's that for that. So I hope the camera extends at this point. Let me give it a check quickly. Yes, it certainly does. So, so all of this is just for the sake of writing that. So I have, this is known as the distance between a point and a plane. I hope you can see something quite interesting. Before I told you the general form. No, let's not go there yet. So when I finish this, I'll show you. So the distance between a point and a plane is equal to whatever that is. So it's ax plus by plus cz minus d divided by this is the interesting part. I've already derived it. This is the interesting part. The interesting part is that magnitude of n is equal to the square root of a squared plus b squared plus c squared, because this is the vector n. So I have that the distance between the point and the plane is equal to ax plus by plus cz minus d divided by square root of a squared. But note though that this has to be absolute value, so you have to make this absolute value because distance can be negative. So distance is the absolute value of this divided by this. If you reduce this by one dimension, so we have distance between a point, reducing by one dimension is turning a plane to a line. So we erase all the z values or all the z variables because there'll be no third dimension. Is equal to ax plus by minus d divided by a squared plus b squared. Really, that's it. That's everything. Now the interesting part is that if you recall, the general form of the equation of a line is ax plus by plus c, right? This is exactly the same thing. So I can write that the distance between a point and a plane is the absolute value of ax plus by plus c a squared plus b squared. Really, that's everything. In this case, it just so happens to be that c is equal to negative d. So in this case, so like this. But no, that here c is equal to negative d. Literally, that's it. So yeah, I reduce this by one dimension to get the distance between the point and the line. Now, for the sake of interpretation, the normal vector for 2 dimensions is going to be the vector you form that's perpendicular to the line at the midpoint, and that will be the perpendicular bisector. So you can use that, and this will be the formula for distance between the point. It's really interesting though, how everything just is so, symmetric. By the word symmetric, I don't actually mean symmetry in mathematics, but it's quite, you can always show from ground principles or from original axioms that some assumption is either true or false in mathematics. You don't have to believe it. You just have to logically show by proofs or by derivations. Well, there's a difference between proofs and derivations. Proofs is annoying. Derivation is quite. Proofs is, yeah, well, I'll get to that later. To be honest, I love mathematics, but I hate proofs. It can really kill you. But yeah, so you don't have to take anything by heart, but like, it should be like this. Just follow the axioms for the logic of mathematics, for the rules of mathematics while using your logic, try to understand what's going on, and then you can either prove that an assumption is true or false, or if the assumption makes sense, or if the assumption is, viable. So yeah, so I've literally showed it. I didn't have an idea. I knew what the formula of the distance between a point and a line was. It's just I didn't know how to show it, how to prove it using those normal two-dimensional rules. So I have to go to three dimensions, which I know quite well. And I showed what a normal vector is. So I'm gonna apologize because maybe some people know, so maybe some people don't know all these terminologies and all these things. So yeah, that's that about that. This is everything in coordinate geometry. That's the end of coordinate geometry. Next thing we're going to be doing is next week, Sunday. So I'm going to start with binomial series. Talk about the Pascal's triangle. And then, yeah, start with binomial expansion. How to prove, yeah, anyway, so yeah. And then after that, yeah, it might take 2 or 3 weeks to finish binomial theorem because of, uni, I guess. So yeah, that's it for today. I've literally finished the whole of coordinate geometry. I'm really liking that I was able to do this from 3 dimensions and then reduce it by 1 dimension, so we can go to 2 dimensions. But then, if you really want to think about it, let's say you wanted to do the distance between a point and okay, so we had plane. So for 1 dimension you have a line. For 2 dimensions you have a plane. For 3 dimensions, it's more like saying, okay, think about this. For 1 dimension, you can't have a circle. It's impossible, yeah. Okay, let's start from 2 dimensions. It's more like saying a circle is just a sphere in 2 dimensions, and it's true. You can say a sphere, or let's say a square, is a cube in 2 dimensions, and it's true. So if we think of a square as a plane, then you can say that you can also find in 4 dimensions, 4-dimensional space in this case. In 4-dimensional space, you can also find the distance between, and it's really funny because the distance between anything and whatever the object is always in 1 dimension. In 4 dimensions, I don't know how it's going to be like that. It's like finding the length of a plane. Well, length is still 1 dimension anyways. So yeah, it's really hard to wrap my brain around it. So you can actually do this for n number of dimensions. But yeah, so this is the general formula. I'm still thinking how it's going to be like in 4 dimensions. For like 4-dimensional space, you have some. The thing about 4-dimensional axes is it's not going to be like, you can only find like level curves or level curves of a 4-dimension. So it's like a rotation sort of like. I can't picture it honestly. I can do it with mathematics, but I can't picture it in my head. It's hard. It's not that it's hard, it's just I can't even think of how 4-dimensional is going to be like. 4-dimensional space is going to be like. But yeah, so that's all for today. I'm still talking. I'm thinking of what else to add to this. Yeah, that'll be all, I guess. So yeah, thanks for watching today's video. Like, share, subscribe, show the people about it. If there are any mistakes, let me know. If there's something that's missing or I'm not too clear about how I do things, let me know, because, well, my aim is to probably go into academia later on. So I said about that. So thanks again for the 3rd time. Thanks for watching. Bye.